Welcome back, mathematicians. So, as we talked about in 2.5, I try to record these lectures. I thought they were beautiful, but unfortunately, my iPad, I don't know where they entered a black hole of knowledge, but they did not record, or they recorded and they just didn't save. So after I cried for a little bit, I'm kidding, we're back in action. So if you liked how the notes were the last few lectures, all written and ready to go, great. If you didn't, I'm sorry. Okay. So 2.5 is all about continuity. What does it mean for a function to be continuous? In like high school, middle school, whatever, you're kind of told that like a function is continuous if I can draw that function without raising my pencil, right? I can draw it on a piece of paper and I can follow it along with my pencil. I don't have to raise my pencil at all. I call that the little kid definition, kind of like a cutesy little way to remember it, but not really the true definition. So let's look at this beautiful pre-drawn piecewise function I've given you guys. The black line is our function f of x. And using our little kid definition, we can see that as we're going along and we're going towards 1, well, I have to pick up my pencil and then start here and then keep going. For 2, I'm going down this line, got to pick up my pencil, draw that point, and then keep going. For 3, I just go up and down, right? That point's already there. I don't need to move. And at 4, I have to raise my pencil again. So I had to raise my pencil at 1, 2, and 4. So we are going to all agree that f is not continuous at x equals 1, x equals 2, and x equals 4. Well, at 3, I didn't have to raise my pencil at all. So f is continuous at 3. These statements are all true with the actual more structured definition of continuity. I'm just trying to show you guys how we get from the drawing, not raising my pencil, to an actual definition. So what's the difference between x equals to 3 and all the other points? Well, at 1, I have a jump, and at 2 and 4, I have holes where the point is somewhere else. Well, 3 didn't have a hole, and there aren't any jumps. So when I don't have a hole, first, when there's no jumps, we kind of already talked about in 2.4, that means the limit exists. So we'll say like the limit is f of x as x goes to 3, that exists. And when there's no hole, that means that my function at 3 equals that limit. Right? So if we scroll down to this definition that I just wrote, we can see that a function f is defined to be continuous at c if the limit as x goes to c of f of x is equal to f of c. Right? We can see that at x equals 3, as I'm going up, up, up towards this value, my function also has that same value. Whereas at 2, I was heading towards this point, but my function value is actually all the way up here. At 4, I'm only coming down from one side, right? If I'm reading from left to right. I'm only just going down here. I'm never coming back from the other side. We say that if this little point actually was right in here, that f of x is right continuous. Excuse me, not right continuous, left continuous, our second point. But if we're just coming at one side, f of x is right continuous at c, also known as continuous from the right, if the right-hand limit of f of x equals f of c, and we also say a function is left continuous at c, or continuous from the left, if the left-hand limit equals f of c. Right, so back to one of our favorite functions, the square root of 4 minus x squared. Its domain is negative 2 to 2. I think we talked about that last lecture. So we saw that the left-hand limit of negative 2 equaled the function value. So we can say that it's left continuous at x equals negative 2, and we can also say that it's right continuous at positive 2. So then we can actually say a few more things about it. So a function is continuous on a closed interval, a, b, that's what those hard brackets mean, closed interval, if it is left continuous at x equals a, and right continuous at x equals b, and continuous at every point in between a and b, right? So we saw that when we drew the picture of the square root of 4 minus x squared. Remember, it's the northern hemisphere of a circle of radius 2, centered at the origin. So we can say with confidence that f of x is continuous on the closed interval negative 2 to 2. How can I, using the definition above of a continuous function, then know if a function is continuous? So we have something called the continuity test. So we say a function f is continuous at a point x equal to c if and only if, remember that, it meets the following conditions. So first, f of c has to exist, right? For f of c to exist, it also kind of has like an underlying meaning. C must lie in the domain of f. All right? So f of x is up here, square root of 4 minus x squared, can't be continuous at 100. It's not, f of 100 doesn't even exist. It's not in the domain. Second condition that needs to be met is the limit as x is approaching c exists, right? I can't have a jump. I have to have my left hand limit and my right hand limit equal each other. That's for when a limit exists. I need those to be true. Thirdly, I need that limit as x approaches to c of f of x needs to equal the function value at c, which is called f of c. For those three conditions to be met, we can say that f is continuous at c. Okay? So if f is not continuous or discontinuous at some x equal to c, then we say that x equal to c is a point of discontinuity. Usually there are points that are discontinuous, that we're discontinuous at. So, spoiler alert down here. Let's go look at the function f of x equal to 1 over x. Right, kind of what we've talked about or not already is, this is the graph of the function. Its domain is negative infinity to 0, union 0 to infinity. So its domain doesn't even have 0 in it, continuous or not. If you already saw, it is actually continuous. The only point of discontinuity is at x equals 0, right? The limit, ooh, I'm getting ahead of myself. But x equal to 0 is not in f of x's domain. That's supposed to be an s. So we can say that f of x equal to 1 over x is continuous on its whole domain. However, that function is discontinuous on any interval containing 0. So if I'm looking at the whole real number line, negative infinity to infinity, then I can't, that includes 0. I'm gonna have to say this is a discontinuous function. Okay? So more fun properties about continuous functions. Remember how we can find an inverse of a function of on an interval, right? So x squared, we can find when x is greater than 0, we can find an inverse. And when x is less than 0, we can also find a different inverse. So the inverse of any continuous function on an interval, so that's what the on the interval means, that inverse is going to be continuous. So the inverse of x squared when x is greater than 0, a continuous function on an interval, the square root of x is also continuous, all right? Well, composite functions of continuous functions are also continuous. So if I put in, what's a continuous function? Sine of x, and then I square it. Those are both, sine x squared is a continuous function. Well, sometimes that's a little bit too strong. We don't need my outside composite function, usually denoted g. I don't need that to be continuous everywhere on the whole in negative infinity to infinity. So we have this awesome theorem. I denote theorems THM, just a quick hand thing. So theorem 2.5.1 states that if f is continuous at c and g is continuous at f of c, then g composited with f is continuous at c. So I don't need g to be continuous at every x. I need it to be continuous at on the range of f, specifically at f of c. Composite functions also give us another theorem, 2.5.2, and it says if f of g is continuous at the point b and the limit as x approaches c of f of x equals b, then I can write the limit as x approaches c of g of f of x as g of the limit of x approaching c of f of x. Basically, I can move the limit inside of g. Well, we know that equals b, so we get g of b. So basically what I'm saying is if a function is continuous, I can move that function inside of it. We mainly use this property for trig functions because we already have the power rule and root rule in our function laws that said I can move, and limit laws that said I can, the root of a function is a function. Okay, that's what I'm trying to say. So example from your textbook in 2.5.31, you're asked to find the limit as x approaches pi of sine of x minus sine of x. So that second sine of x is still within sine. Alrighty? That's not a typo. We know that sine of x is a continuous function, and we know it's specifically continuous at x equals pi. So remember, when you're doing your homework later, I don't need it to be continuous everywhere. I specifically need it continuous at wherever my limit is going towards, right? Because tangent, secant, the other trig functions that have something in their denominator, those aren't going to be continuous everywhere, but might be continuous at wherever you're heading. Okay? So, since sine is continuous, I can move my limit to the inside. So I have sine of the limit as x goes to pi of x minus sine of x. Well, sum and difference says that I can just take the limit as x and take the limit of sine of x. So since sine is continuous at pi, I can just plug in pi. So that's how I get sine of pi minus sine pi. Sine of pi, since you guys know your unit circle so well, that's just 0. Sine of pi minus 0 gives me sine of pi, which is again just 0. So that's how we can use theorem 2.5.2 to correctly give us the limit of that function. Alrighty? So continuous functions also have this awesome property called the intermediate value theorem, or intermediate value property. I was also very proud of this picture that I drew. I drew it in real time, so I'm really sad that video is lost. If this video is lost, I will be so sad. So if f is continuous on a closed interval, say AB, and if y naught, just some y value, is any value between f of a and f of b, then f of c equal to y naught will exist for some value between a and b. I think I missed the word exists. So basically what I'm saying is that if you look at this picture, again, should be the MoMA, maybe even the Louvre. Black is my function. If I start here at A and I go down and up and down again a little bit and get to B, if this function value y naught is in between f of A and f of B, there should be a function, a value that I can plug into my function to get to y naught. So it's also kind of saying that like I'm touching every point in between f of A on my way to f of B. Right? Like if I use a little kid definition, I can say that as I am not picking up my pencil on the curve, I'm going to hit every point in between. Well, like, duh. So like, it kind of seems like a redundant theorem, but it's not. It's actually pretty useful. It's very useful when we're actually finding roots of functions. Remember, a root of a function is when f of x equals 0. The solution to that. A lot of the problems that I work with, applied mathematics works with, is solving when functions equal 0. Because usually if you want something to equal something else, you can subtract it to the other side and you get a function equal to 0. So the intermediate value theorem is actually really important in high level math, even though it seems kind of like obvious. All right. So how do we find roots with it? Let me show you in an example because I think that's the best way to do it. So in this example, you have f of x equal to x cubed minus x minus 1. We want to show that there is a root between 1 and 2. So f of 1, I'm going to plug 1 in. I'll get negative 1 back out, right? 1 minus 1 minus 1, negative 1. Then I plug in f of 2, and I get 2 cubed minus 2 minus 1, which gives me 5. So in this case, since we're trying to find a root, and that's when f of x equals 0, my f naught should is basically saying 0, right? I am starting somewhere below the axis because I have a negative number, right? F of 1 is less than 0. And then at 2, f of 2 is 5. So at some point I have to cross the axis, which is when my function, that's a root. This is when f of x equals 0. All right. So we're kind of already given slyly that polynomial functions are continuous. If you remember, the limit rule said that if p of x is a polynomial, the limit as x goes to c of p of x is just p of c. That's just the definition of a limit. So pretty sneaky right there. You're kind of already given some definitions for things that you didn't even know. So we know that all polynomial functions are continuous. Remember, polynomials are when the power is positive, not negative. So that implies that f of x is continuous. So I have my function going from negative 1 to 5, and I want to make sure that I'm going to hit 0. Well, f is continuous, so by the intermediate value theorem, f of x has to have at least one root in between 1 and 2. And that's all. That's all you need to say. Just say that there's a number less than 0, a number greater than 0, so I have to hit 0 because f is continuous. All right, so remember how we said, f divided by, no, what am I saying? F of x equal to 1 minus x is continuous on its natural domain, but not on intervals that include 0. Can we make some functions similar to 1 over x so that it's continuous over all numbers, meaning negative infinity to infinity? We actually can't, because the limit as x goes to 0 of that function doesn't exist. Remember, from the left, I'm going down. From the right, I'm going all the way up into infinity. It's not bounded. That limit doesn't exist. Well, what about sine of x over x? Let's call that one g of x. I know that limit exists, and its domain is the same. It's actually infinity to 0, union 0 to infinity. That's the same as the domain from earlier. And I know the limit exists. So I have a limit exist at that point of discontinuity. So now I just need to think of a way to make it pass the continuity test. So we said that we can construct an extended version. So we actually don't say that. I don't know why I kept writing that. So we can construct a continuous extension of g of x equal to sine of x over x, such that over the whole real number line, all the real numbers from negative infinity to infinity, we can have this big g of x, and we can call it sine of x over x when x doesn't equal 0, and 1 when x does equal 0. Well, I know the limit exists. We've shown that already. And I need to make sure that big G of 0 exists. So I plug it in. Well, when x equals 0, my function equals 1. That's what the piecewise function says. Well, that also equals my limit. So by the continuity test, big G of x is continuous. So suppose the limit, we have a definition. Suppose the limit as x goes to c of f of x equals L. But f of c is not defined. Then we can call big F of x the continuous extension of f if big F of x is defined to be little f of x if x is in the domain of f, and L when x equals c. This might not take care of all discontinuities. You might have to have like a few lines if there's more than one discontinuity, but if we're just focusing on one point, then this will be the continuous extension. All right, so let's just look at a cute little polynomial, right? I think we've kind of all experienced finding limits for these. So we have the f of x equal to x squared plus x minus 6 divided by x squared minus 4 when x does not equal 2. So we're asked to find the continuous extension at x equals 2. Well, I can factor the numerator and the denominator. I'll get x minus 2 and x plus 3. I don't know how you guys like to factor. I find things that multiply to negative 6 and then add to 1, excuse me, the coefficient of x. So that's how I got negative 2 and 3. And then the denominator is from sum of squares, or sorry, difference of squares. So I get x minus 2, x minus 1. The x minus 2 functions cancel out. That's how I can get x plus 3 divided by x plus 2. But remember, this is still little f of x, so x still can't equal 2. Well, then I can just call big F of x, x plus 3 divided by x plus 2, and just not include that mumbo jumbo about x not equaling 2. Okay? I could have also made a piecewise function and done that, but this was kind of more convenient to just say that part of the function. All right? So let's do a problem from your book, and then I think we should be done. Okay, cool. So 2.5.44 asks what value of b is g of x equal to x when x is less than negative 2 and bx squared when x is greater than or equal to negative 2. Continuous at every x. Every x implies from negative infinity to infinity. So note that x and bx squared are continuous everywhere, right? So the only place where it might not be continuous is at x equals negative 2. We have a line and a parabola. I need to make sure that my pencil doesn't take off of the graph, so I need to make sure that at x equals negative 2, they connect, okay? Well, continuity says I need to have those three conditions. So I need to know that f of c exists. So I plug in -2 into g of x. So that gives me b times -2 squared, which is just equal to 4b. Then I need to make sure the limit exists. Oops, there we go. So the left-hand limit, when numbers are less than -2, I'm going to be using x. So the left-hand limit of g of x as x approaches -2 is the same as the limit of x as x approaches -2 from the left. That's just going to equal -2. So then we have the limit as x approaches -2 on the right-hand side of g of x. On the right hand of -2, we have b times x squared. So we just showed that that was 4b. Well, I need this to equal -2, right? I need the left-hand limit to equal the right-hand limit because I need that limit to exist. So I set -2 equal to 4b, divide by 4, and that's how I get 1/2 b. I can do one final check and make sure that both of those things are now equal. I plug in -2, I get -2. Well, that's the limit. We're good to go. So now we can say with confidence that b is equal to -1/2 allows g of x to be continuous at every x. All right, I hope this was helpful for you guys. I hope you learned a little bit, hopefully a lot of it. I'm sorry if you didn't like that these were pre-written and I might have talked a little too fast. But hopefully next week we will figure out this recording stuff a little bit better. You have a quiz today that opens and you have your first homework due, so please turn that in, and I will see you guys next week.